So as we saw, separation of variables on Laplace's equation on the disk led us to this periodic boundary value problem with this guy right here. So let's see. So what about the case lambda negative? Well, if lambda is negative, then we know that the general solution for this equation would be something that looks like e to the actually, let's give it a coefficient. A e to the minus theta root lambda plus b e to the minus theta root positive root lambda. And that is not periodic, so it's not going to fit the periodic boundary conditions. We could look for solutions when lambda is equal to 0. In this case, we get g is going to be a plus b times theta. And that's not going to be periodic if b is non-zero. But if b is equal to 0, then it actually works. So we'll take g0 of theta just to be some constant function. And then we look for positive spectrum. And we find that, so in this case, we can put lambda equal to p squared. And the form of our solution will be a cosine theta p plus b sine theta p. And if we differentiate it to check the derivative boundary condition, then this is going to be minus a p sine theta p plus bp cosine theta p. And so evaluating these boundary conditions, we have, let's see, so at g of 0, for instance, we're going to get a times 1 plus b times 0. And then g of 2 pi is going to give us a cosine 2 pi p plus b sine 2 pi p. And then doing the same thing for the derivative, we end up with minus a times 0 plus b times 1 is equal to minus ap sine 2 pi p plus bp cosine 2 pi p. And so this is a 2 by 2 linear system, so collecting the coefficients, I've got cosine 2 pi p minus 1, and then I've got a sine and a minus sign, and then with a p, and then I've got a p cosine 2 pi p minus 1. And so the system looks like this guy multiplied against a b gives us, and then the coefficients are left at 0. So we've got a homogeneous system, ax equals 0, and the only way that that can have a non-trivial solution is when determinant of a is equal to 0. So let's take the determinant of this guy. So determinant of this thing, which I will just grab, lamb, there we go. So the product coming down the main diagonal here is going to give us p cosine squared 2 pi p minus cosine 2 pi p. And then the product coming up the other way, since it comes with a minus sign, that'll cancel the negative p. And so we've got p sine squared 2 pi p. And then this cosine squared and this sine squared are going to give me minus 1, or going to add up to give me 1. So I have 1 minus cosine 2 pi p. Somehow I'm off by a factor of, what did I do? Oh. Okay, yeah, there it is. Okay, so, sorry, so when I evaluated this one, that's not a 1, that's supposed to be a p right there. And so then that means that this is a p here, and this is 1 here, and then there's 1 there. And now there's a common factor of p that I can factor out of these ones. Okay, great. Okay, so this is going to be equal to 0 then if 2 pi p is a point where cosine is equal to 1. And so cosine is equal to 1 at 0 and 2 pi and other integer multiples of 2 pi. So I need p to be an integer, except we're looking at the case of positive numbers right now. So I need p to be 1, 2, 3, and so forth. And so with that in mind then, I get a spectrum. Lambda n is going to equal n squared, and corresponding eigenfunction gn equal to an cosine n theta plus bn sine n theta, and that's for n equals 1, 2, 3, and so forth.